Yeah, definitely I'll come to your school whenever it is possible. I definitely come and meet you personally. The first batch of JNV Ramnagar student, class 11th. I'll keep in mind. So, what we have studied, we have studied the wave mechanics, and we have started the wave mechanics specifically. So, in wave mechanics, in the previous one lecture, we have studied that how a wave function is obtained, okay, and how to differentiate that this function is wave function or not. Yeah, I'll definitely come for sure. So in the previous lecture, what we have studied the wave function. Okay, how a wave established by a source. Got it? And with the help of this function, that is y is equals to f of x and t, that we have already discussed, that why the function, why the variable, why the displacement in the wave depends on the position as well as the time. Got it? And then we finally arrived on a conclusion that a partial differential equation del 2y by del t square equals to v square into del 2y by del x square is the final wave function equation. Okay. So any function who satisfies this equation will be considered as a wave function, and rest of the other is not considered to be the wave function. Got it? So I hope you have attended the lecture and you have remembered it, that what we have done. So today's topic that we are going to ace is equation of simple harmonic progressive waves. We are going topic wise topic because this wave chapter itself is very complicated with the perspective of student. Okay. So what I'm doing is I will make the concept very crisp, take the session very crispy sessions, not too lengthy, not too bulky sessions like 4 and 5, 3 or 4 concept in one lecture. No, I will just discuss 1, 2, or hardly 3 concept in one lecture, so that you will grasp what a wave is, why we studied it, and the question that you will given, you will tackle that question. That is my ultimate aim. So today our aim is to establish a equation of simple harmonic progressive waves. So we have studied waves. The waves are two different types of wave: mechanical wave, non-mechanical wave. Let we revise it with me. Okay. So we revise it together. We have two types of wave. First of all, what is a wave? Wave is a disturbance. Disturbance of what? Disturbance of momentum, disturbance of energy. Okay. That is a wave. Or disturbance of any particular physical quantity, like in terms of pressure, electric field, magnetic field. That particular thing, that disturbance which travels from one place to another place is termed as wave. We have studied it. Okay. Now, then the question arises that how many types of wave we have. So we have only two types of wave: mechanical wave, non-mechanical wave. Okay. Mechanical wave, non-mechanical wave. Mechanical wave, which are wave those required a medium to travel. The wave which requires a medium to travel, like I'm talking to you, you require a medium to listen to me, na? So that wave is a mechanical wave, and that is a sound wave. I'm producing sound with my mouth that is reaching to your ear by some medium. So that sound wave is a mechanical wave. So the wave which required a medium to travel from one place to another place is termed as a mechanical wave. And the rest, which does not require any medium to travel, is termed as a non-mechanical wave. Like the sun rays is coming to earth, sunlight ko we can consider a wave. Okay, we will consider it a wave because it behaves as a wave, electromagnetic wave. But between sun and earth, there is no medium in between them. There is totally vacuum. So how it is possible for a wave to travel from vacuum to earth? Okay. So which means that this wave, this particular kind of wave, does not require any medium to travel. So that we have categorized in non-mechanical wave. Okay. Then we have discussed that what a wave function is. Okay. Let me just show you the slide that what we have discussed. We have discussed this function y is equals to f of x in t. And how we have derived it? So we have considered a wave in a string. This is the displacement y with respect to the x. Now, the source particle, which is at x is equals to 0. Here we have the source particle. This source particle is oscillating. I'm not saying that it is in SHM. I'm saying that it is oscillating. Oscillation doesn't mean SHM. SHM is the simplest case of oscillation. Okay. Let me first thing we conclude here that it is oscillating. Due to these oscillation, there is a disturbance of displacement. Here, the y is varying because this source particle is continuously changing its position with respect to this x is equals to 0. This same disturbance travels further, that form a wave. So this wave is nothing but the disturbance produced by this source particle. Source particle. Now, based on that, now it is very easy to conclude that how the source particle is oscillating. We can categorize the wave in two categories. If the source particle is oscillating perpendicular to wave motion, there are two possibilities only. It can either perpendicularly travel or oscillate with respect to the wave motion. Wave is traveling in this direction, you can see. And another way that it can travel along the wave. Okay. Second one is along the wave. Along the wave. So in the wave in which the source particle oscillate perpendicular to the wave motion is termed as transverse wave. We have studied it. And in which the particle oscillate along the wave, like wave motion is in this direction, so particle is also oscillating in the same direction in which the disturbance is traveling. That wave is termed as the longitudinal wave. Longitudinal wave. I have also told you that this graph specifically does not belong to a longitudinal wave. It is now representing a transverse wave here. But the same graph we can plot for longitudinal wave also. Okay, I have told you. Now, this disturbance I have already told you that what can be this disturbance. Yeah, this displacement. So this displacement can be pressure, density, okay, electric field, magnetic field, whatever. Got it? Now, if we want to know, let's say we have consider a particle here, or we just don't consider a particle. Let me ask a question to you. Find the wave function or write the wave equation of this particular graph, which is shown in the figure. So what will you say? And let's say each particle is oscillating. So what will you say? The first question that arises in your mind, that where is the point? For what point we have to write the displacement? Okay, that will be your for sure the first question. Where is the particle? For which particle we have to write the displacement? So x is important. That is why this y firstly depends on x. Now what about t? How it is depending on t? Let's say I have told you that at x is equals to 2 centimeter, whatever the particle is present at x is equals to 2 centimeter, you have to write the displacement of that particle. And let's say 2 centimeter is here, from here to here, it is 2 centimeter. So here the particle, this one. And this is the displacement from mean position. Let's say yp. Now, when you reach at this particle, what you will find that this particle is also oscillating with time. The displacement of this particle depends on the time also. At what time we are seeing it? What it? Because it is in oscillation. It is oscillating. Continuously it is changing its position with respect to time. So that is why it is very important to know that what at what position and at what time the particle is in a particular wave, so that we can know the exact displacement of that particle from the mean position. So that is why this time is also important. That is why we have written that y is a function of x and t. More specifically, this y belongs to a function of type ax plus minus bt. Got it? Now, two important thing I am going to tell you here, and you have to note it down. First, how to determine how to determine where, in which direction, sorry, in which direction the wave is traveling. Wave is traveling. Okay. Either it is going in plus x direction, positive x direction, or it's going in the negative x direction. So for that, keep this function in mind. Y is equals to f of ax plus minus bt. Got it? Now, if both ax and bt have same sign, same sign, so wave is traveling in negative x direction. Wave is traveling in negative x direction. Okay. But this is the first A case. B case is if ax and bt have opposite sign. Opposite sign. So wave is traveling in positive x direction. Got it? So this is it. Now move on to the next one. This is the equation of simple harmonic progressive wave. Now, how this wave is formed? So this is very simple. We have this string is oscillating, got it? And here the x is equals to 0. The displacement axis we will give as y, and this is x. Got it? Now, I have told you that each and every particle in the string is oscillating. There are various particles which are in oscillation. They are oscillating about their mean position. Okay. But if the oscillatory motion is SHM, if, focus on my word, if the oscillatory motion is SHM, then that particular wave is termed as equation of simple harmonic progressive wave. Got it? So I will write it as not point here. We know that each particle is in oscillation in wave. In wave. But when each particle, or instead of each particle, writing each particle, we will write when source particle from where the disturbance is generated. When source particle is in SHM, then that wave is termed as what? That wave is termed as simple harmonic progressive wave. Simple harmonic progressive. So any kind of doubt do you have how this simple harmonic wave is defined? We know that source particle is oscillating. If it is oscillating, we have told that this is a wave, simple traveling wave. But if the oscillation itself is SHM, we know that the simplest case of oscillation is SHM. So if the source particle is doing simple harmonic motion, so the disturbance that will be formed will also be in simple harmonic motion, because in wave each and every particle is following what the source particle is doing. So if the source particle is doing to and fro motion, so the disturbance, the another particles present in the wave will also do the same to and fro motion. If the source particle is making a square wave, the rest of the other particle will also make a square wave. If the source particle is doing SHM, then rest of the other particles will also do SHM. And that particular case of wave is termed as simple harmonic progressive wave. I hope you got it. If you have any kind of doubt, you can put the message in the chat box. So now what our job is? Our job is to find out this expression. This expression is y of xt. The wave function is this because it depends on x and time both, equals to a sine omega t plus minus kx plus phi. Okay. So this is the equation of simple harmonic progressive wave. It is looking like a simple harmonic motion. If the kx is been removed, this equation is the simple harmonic equation. Okay. So we have to establish this equation. Now, just a second. Yeah. So we will consider this is a wave. This is the wave. This is in x direction, which is moving from here to here, like this. Just a second. Okay. This is x. And this is the disturbance y. Got it? Now, if this is the source particle which is at x is equals to 0, this is the source particle from where the disturbance is coming. Okay. When you tied up the string and do this motion, your hand is the source particle in that case. Okay. So source particle is SHM, doing SHM. Now, if I want to find out the equation of this point, let's say this is the point P here, and displacement of this point is YP. So this is some general point in the wave. So if I able to establish the displacement for this point P in this form, so I'll be able to establish the equation for all the points. This is the general point. So we just have to find out the displacement of this particle which is present at this point here. Got it? And let's say this distance that it has traveled on x-axis is small x. And wave is traveling with a speed of v. This total wave, complete wave is traveling with a speed v, and this particle which we have considered is at position x. Okay. Now, we know that if y is a function of x and t. Now, listen to me carefully. We want to find out the oscillation, or we want to find out the equation of this yp, displacement of this particle. Got it? Now, if I put x is equals to 0 in this expression, in this function, if I just put x is equals to 0, which means I am talking about the source point, and source point is doing SHM, which means we just have to write the equation of SHM for source point, and that is y of source is, we can write a, let the amplitude is a sine omega t plus phi. That could be the equation. Okay, for x is equals to 0. For x is equals to 0 means we have at source point is doing SHM, and the equation of SHM is this. So this ultimately represents the wave, because here the value of x is 0. The value of x is 0. So this ultimately represents the equation of wave. Okay. But here, this particular y is the displacement of a particle which is at source point. This one. Now, whatever the source point is doing, same is going up, same is going forward. Okay. Which means this same disturbance, sometime before it was at source. Got it? Are you relating what I'm saying to you? This source point is oscillating in SHM. It is establishing this disturbance. This disturbance is moving forward. But who has created this disturbance? The source point. So let's say this disturbance moved a little here. At some time before this disturbance hit at the source point. Got it? So what I want to try to say you that this displacement yp sometime before is at the source point at here, because source is also doing SHM, and that disturbance is traveling further, which means sometime before that particular displacement that we are talking about at point P is at origin. Have you got it? Each and every one. When you will answer to this question, then I will move further. Got it? What I'm trying to say that this particular position or this particular displacement is some time before it is at this point, at some time before it is at source point. So if we are able to write, because we can write the equation of source particle. Okay. So if somehow we relate the source particle displacement with this particle displacement, so we are able to find out the equation. Got it? Now we will write yp, displacement of this particular point. Now we can say that at time t is equals to t, this particle is at this position. We are not saying that it is moving up or down. It is at yp. The displacement is yp at time t. So how many time before this particular displacement is at origin? So for that, what we can do, this particle is at a distance x, and how much time it will take to travel x at that time before it is at the origin. Suppose, just a second, if this is the wave, after some time, after time t, this wave is shifted like this. Got it or not? After some time, it will get shifted. So this point has moved this distance. This point has moved this time, this distance. This point has moved this much amount, this much amount. So we can say that this point P, let's say this uh, disturbance, this this yellow color disturbance is at time t is equals to 1 second, and this P, red color disturbance, the same particle, is at t is equals to 3 seconds. So what we can say, can we not say that this point P at 2 seconds before it is at this point? So same thing I want to convey to you in the example in the previous in the that we are discussing in the slide, that if this is the source, if this is the particle yp, so this particular displacement sometime before it is was at origin, it is at origin. We can do that because if you talk about this point is shifted in time t, let's say at this position. So at t time before, where it was at point A, and this is point B. If I talk about this particular position, let's say this, okay, and I'm going to ask you, this is position C, and here the displacement is YC, and this is the same position, it is just shifted here, C dash, and the displacement is same, YC, and the time taken by it is time t. So if I'm going to ask you that whatever the particle is present at C dash at t time before, where it was at B, A, or C. Tell me in the chat box, each and everyone, student of JNV Ramnagar, do it. I'm asking that this disturbance has taken time t from C to C dash. So this C dash before time t, where it was? Tell me. Very good. It is at C. So in the same way, if I'm telling you that this particular point at particular time t, it is at yp, and it has covered x distance with a velocity v, the disturbance is traveling, so you can assume that this particular displacement is also traveling with a speed v and have covered x distance. So how much time it have take? So time taken by it will be x by v, because velocity is x upon t. So how much time? This is not t. So time that it has taken here is x by v. Very good. So x by v time before it was at origin, and now it is at time t. Or this is this time t, and this time is different. Okay. So how much time before it was? So it is at t minus x by v. At particular time t, it is at yp. And x by v time it has taken to reach yp. So how much time it has taken? In the same example, the displacement is at t is equals to 1 second. Same displacement has at time t is equals to 3 second. So what is the time difference? So you have to subtract it. 3 minus 1. So यहाँ पर जो time है, the time is here is t, and the time it has taken from origin to this point is x by v. So what is the total time? What is the difference of time? It is, so in the same way, if you put a sine omega t minus x by v. So this is the equation of displacement at particle P, which is at origin at t minus x by v time before, plus 5. Okay. Now yp here equals to a sine. If you multiply these inside, it will become omega t minus omega x upon v. Omega x upon v plus 5. Okay. Now put the values. It is a sine omega is nothing but 2 pi by capital T into small t minus, again put the value of omega. It is 2 pi by capital T into x upon v. V ko you can again put, what is v? V is the wave velocity, and it is given by lambda by t plus 5, because v is the wave velocity or speed. So wave velocity or speed is defined as the time that it has taken to complete one wavelength, okay, or one oscillation. One oscillation automatically mean the, you can relate with wavelength. So how much time it will take to complete one oscillation? The time period, capital T. And in one oscillation, how much distance it has traveled? It is wavelength. So lambda by T. Now this T and T will cancel out. So what do you have? That yp is equals to a sine 2 pi by capital T into T minus 2 pi x 2 pi x by lambda plus 5. Okay, so this is the form. Here you can see that here y is the function of x and something you can write as ax minus bt, or you can say bt minus ax. So I have told you in the very first slide. Let me show you. If both ax and bt have same sign, so wave is traveling in negative direction. And if ax and bt have opposite sign, so they are traveling in positive x direction. So tell me, in which direction the wave is traveling? By looking at this expression, consider 2 pi by t as b and 2 pi by lambda as a. So they are of opposite sign, which means that our disturbance is traveling in positive direction, and that's so we have considered. We have considered that a wave is traveling in positive x direction. So this will also align with our conclusion that we have made in the previous slide. Got it? I hope you got it. Now various form of uh, wave equation you can write. You can write if wave is moving in negative x direction, so what will happen? This will convert it to same sign, 2 pi by capital T small t plus 2 pi by lambda x plus 5. Okay, so this is it for negative, or I will say negative x direction. Got it? And this is for positive x direction. Got it? Now, we also know that in the previous lectures we have did that 2 pi by lambda is nothing but what? What you can say? 2 pi by lambda is the small k. 2 pi by lambda equals to small k, and which is nothing but wave number. I have already told you about this. What are the physical significance, or what is just the significance of this wave number? Wave number shows you that how compact the wave is. If wavelength is high, which means wave is spreading. If wavelength is low, which means k is high, which means the wave is more compact. Okay, that is all. Now, if you modify this with 2 pi by lambda, so you can say yp is equals to a sine. You can write it as omega t plus minus kx plus phi. So this is the final wave equation. This is the equation of simple harmonic progressive wave. Okay, hope you got it. Now, what is phase and phase constant? So it is very simple. We have the equation now. Y is equals to a sine omega t plus minus kx, or specifically we will take minus omega t minus kx plus phi. So in this equation, this is equation number 1. Omega t minus kx plus phi itself is termed as phase. This is phase. And in the same way, it tells about the status of a wave. Okay. Specifically, it will tell you about the position status of a wave, status of particle, which is its wave motion. Got it? When you put when t is equals to 0 and x is equals to 0, at that particular time, what is the value of this y? What is the value of this phase? Is only phi. This phi will become phase constant. Phase constant. So when t is equals to 0, x is equals to 0, value of phase will become phi. So it will tell you about the initial status of what particle will be situated at x is equals to 0. It is source particle. So it will tell you the initial status of source particle. Got it? Now, we will talk about the particle velocity and acceleration. Now, this y is equals to a sine omega t minus kx plus phi. Now, this is the displacement of a particular particle. Okay. If this is a wave, so this y represents the displacement of the particle which is at x distance away from origin, x is equals to 0, and at time t. This is y. Okay. Now, if I want to know the velocity of this particle, we are only interested because x is fixed for this particle. X is not changing for this particle. Only with respect to time, it is moving up and down. So y will only depends on time. Got it? So I will write it as not here that the value of x is fixed for what? For a particle which is in wave motion, which is in SHM, I will write. So to know the velocity, what we will do? We will differentiate this displacement, but here the y we have as a function of x and t. What we will do? We will partially differentiate it with respect to time. So what we will get? We will get a omega cos omega t minus kx plus phi. This is nothing but the Vp or particle speed or velocity. Specifically, we will write velocity. If you take the mod of it, it will become speed, particle velocity. This del y by del t is important. Okay, so you have to differentiate considering time is only the variable, rest other are the constant. For acceleration, you need to differentiate it twice with respect to time, but partially. So again, it will become minus a omega square sine omega t minus kx plus phi. Okay. Now, this a sine omega t minus kx plus phi is y. So this will become minus omega square y. So it is satisfying the condition of SHM also. This is the acceleration of particle, where it depends on the negative of displacement. Got it? Now, one thing which is important here, let me tell you here. Yeah, the displacement yp is, or not specifically p, y is a sine omega t minus kx plus phi. From this equation, del y by del t represent the particle velocity Vp, which is a omega sine omega t minus kx plus phi. If I differentiate this function y with respect to x, but partially, so what will I get? Del y by del x is equals to minus ak, this is small a, ak, because now this will differentiate cos omega t minus kx plus phi. This del y by del x, what does it represents in a wave? At this particular point, let's say the value is x in x direction, and the value is here, displacement is y. So del y by del x represent the slope at the particular point. So this is the slope of wave function. Wave function. Okay. Now, if you divide del y by del t with respect to del y by del x, what you will have? You will have a, yeah, this will also convert it into cos a omega cos omega t. So it will become a omega cos omega t minus kx plus 5 divided by minus ak cos omega t minus kx plus 5. Okay, this will cancel out. Omega and sorry, a and a will also cancel out. So this del y by del t is nothing but what? This del y by del t is the particle velocity. Del y by del x is the slope. It is minus omega by k into del y by del x, which you can say that particle velocity is the negative of omega by k. K is the wave number here. So omega you can also put in terms of time. Then time you can put in terms of wavelength. Okay, something like that. So this will become minus omega by k times slope of wave function, which means to determine the direction of where the particle is going up and down, we will decide it with this formula. Okay, let me talk about this particle. So here the slope of the particle is positive, so velocity of the particle will be negative, which means this particle is moving down. Okay. So this is very important. Try to note it down. Now move on to the next one, the speed of a traveling wave. Now we know that here that y is equals to a sine omega t minus kx plus 5. This is the displacement equation of wave. Now let me consider that this wave is traveling in this way. This is x and this is y. Now let me say we will consider two particles here which is of same phase. This wave has shifted somehow further, and let's say this displacement is delta x and this is also delta x. So we will consider these two crest point which is obviously in same phase. So after traveling delta x distance, they are also in same phase now at the same point, and time that they have taken is delta t. So what we can say, this omega t minus kx equals to omega t plus delta t minus kx plus delta x. Plus 5 and plus 5 you can consider because they are in same phase. Initial phase are same for those. So we will cancel it out. Now omega t minus k delta kx equals to omega t plus omega into delta t minus kx minus k into delta x. Now this kx and omega t will cancel out. What you left with is omega into delta t equals to minus k into delta x. So here this delta x by delta t is nothing but in the x direction, the wave is moving. So this delta x is the change in the displacement of wave with respect to change in time. So this delta x by delta v represent the velocity or the speed of wave, specifically speed of wave, which is omega upon k, magnitude wise. Okay. So this is the simple expression for this speed. I hope you got it. Till now, we have covered up to the speed of traveling wave. In the next lecture, we will see the wave on a string and how it will depends on the elastic behavior of a material and the inertial property. And also we will going to see that how this traveling wave in a string or in a particular medium in gas, solid and liquid, how this will depends on the pressure and how it will vary. The speed of sound wave will vary with respect to temperature also. We are also going to see the Newton formula for speed of wave in gas and then the correction made by Laplace in Newton formula, okay, in traveling for the wave velocity in gases. So this is it for now. I hope you got it and enjoying this session. So if you have any kind of doubt, you can ask right now. Otherwise, the lecture is being over. Thank you so much for being attentive. Take care of yourself. Bye bye.